This video is for review quiz P.3, and this is all about radicals and simplifying radical expressions. So we have this first expression, use the product rule to simplify, and the product rule just says that if you have two radicals that are the same power, in these cases they're both square roots, if they have the same power, you can combine the radicals into one radical by just multiplying the inside arguments. So we have 6x squared times 54x and the square root of all of that. And we can do this because now we can combine the numbers into one kind of statement, which will allow us to hopefully reduce this radical even further than we could before. So 6 times 54, not too sure what that is. 6 times 54, 324. And x squared times x is x cubed. So that is our new radical, and now we can simplify. You always need to simplify radicals because the simpler radical is much easier to work with. It also allows you to do more things with it than you would be without simplifying. So the way we can do this is use factoring trees. Get a little room on the right here. So I'm going to take 324 and ask what times what makes this. Well, we actually already know it's 6 times 54. And now I can ask what times what is 6. It's 2 times 3. 54 is, let's see, mind blank. I think 9 times 6 is 54. 9 times 5 is 45, yeah. And 9 is 3 times 3. 6 is 2 times 3. And all we're trying to do here is ask what are there pairs of things. This is a square root, meaning there's a 2 here. So we're looking for groups of 2, or in other words, pairs. And we have a pair of 3's here, a pair of 3's here, and finally a pair of 2's here. What I should actually do instead of this is draw in different colors. We have a pair of 2's, a pair of 3's, and another pair of 3's. Now, each pair means that a single number goes on the outside. So 2 goes on the outside, a 3 goes on the outside, and a 3 goes on the outside. And since we used up all of the prime numbers that result from the root of this thing, that means there's no number left on the inside. We can do a similar process with x cubed. X cubed is x squared times x, which is x times x. We have a pair of 2's that comes on the outside as an x, and we have a solitary x remaining. Therefore, it stays on the inside. It does not come on the outside. The only thing on the inside is that single x. Now we can simplify the statement. 2 times 3 is 6, times 3 is 18, x times the square root of x. And what we've done is we've taken out perfect squares on the outside, or from the inside onto the outside, and we've simplified the statement down. Another way of doing this without using the factoring tree is to ask, is there perfect squares inside of the radical? So we have the square root of 324 x cubed, and if you take 18 times 18, you get 324. So 324 is a perfect square. I can rewrite 324 as 18 squared. X to the cubed is x squared times x, and x squared is a perfect square. And now I can break up the radical going the inverse way. What I did up here was I combined them into one radical. I can go the other way and break this radical up over each part. You get the square root of 18 squared, the square root of x squared, and the square root of x. The square root of 18 squared is 18. The square root of x squared is x. And the square root of x is still there. And you can see these are both the exact same. So it's two methods for doing the same thing. Whichever method makes more sense to you, do that method. It's going to be easier for you. So this is our answer. Let's check it. and it's correct. Right, this is very similar. The previous problem we had multiplying radicals. Here we have dividing radicals, and we can do the same process. We can combine the radical into one thing. That's because if you have like powers on the radicals, like we do here, they're both square roots, we can combine it into a single radical. Okay, now we can reduce this thing down. 192 divided by 3, it's going to go in there 6 times, 12, so 64. X cubed divided by x is x squared. And this one's nice and easy because 64 is a perfect square, and x squared is a perfect square. 64, the square root of that is 8, and the square root of x squared is x. So we didn't need to do the factor tree. You can, if you don't see that 64 is a perfect square, you can always do the factor tree, but it's helpful if you know a little bit of squares because then that'll work out much faster for you. And that's correct. Okay, here we have two radicals that are subtracting, and you can only combine radicals if they're like terms. And a radical is a like term if it has the same radical, namely the same power, so these are both square roots, so that's fine, and the same argument. The argument is the inside thing. Here we have 75x, and here we have 27x. These are not the same thing. However, we can simplify the radicals down and see if they become the same thing, because then we could combine them. The first thing I'm going to do is I'm going to simplify these radicals into the smallest terms. So 75 is 25 times 3, and 25 is 5 times 5. We have a pair of 5s and a solitary 3. The 3 stays on the inside, and a 5 comes on the outside. Okay, 27 is 9 times 3, and 9 is 3 times 3. We have a pair of 3s and a solitary 3. So a 3 comes on the outside, and a 3 stays on the inside. Of course, the x is the same in both of them. There's only a single x in there, so there's really nothing we can do with that. And now you see that these radicals have the same radical and the same argument. Therefore, we can combine them. 5 minus 3 is 2 times root 3x. So that's how you can combine them. You can only do that if they have, if they're completely simplified. So that's why we like to simplify them down. It's easier to work with. It tends to be easier to work with. All right. So this one has the 7th root of negative 1 over 128. So this is not a square root. This is a 7th root. And the 7th root is asking what thing times itself 7 times gives you negative 1 over 128. If you don't know, just break it up over the different parts. So I can first notice that negative is the same thing as negative 1 times this fraction. And I'm doing that because the square root of negative 1 is very easy to find. If you take negative 1 and times it by itself 7 times, you get negative 1. So the square root of negative 7, or sorry, the 7th root of negative 1 is negative 1. If it's an odd power, it's going to be negative 1. If it's an even power, it's going to be 1. Or sorry, no. If it's an even power, you can't do it. It becomes complex, which we'll talk about in later videos. But this one becomes negative 1. And this one, I can rewrite this. I can break it up over the top and bottom. The 7th root of 1, again, 1 to any power is 1, so 7th root of 1 is 1. And 128, I'm pretty sure 128 is the same thing as 2 to the 7th power. The 2 to the 5th is 32, yep. 2 to the 7th is 128. So the 7th root of 128 is just 2. You can try it in your calculator to see if that works out. If you don't know how, we go to the second. This right here says y is x, the yth root of x. And you do that by taking 7, the yth root of x, of 128. Nope, I think I did something wrong there. Let's try the other way. Yeah, it's the other way around. That's kind of weird that they'd have it that way though. So the 128th yth root of 7, so 7's the yth root. Hopefully that makes sense. It's just a way that this calculator works. But either way, 2 to the 7th power, you can always do it this way. 2 to the power of 7 is 128. So that's how you know that that's 2. Of course, -1 times that is -1/2. So -1/2 times -1/2 times -1/2 times -1/2. That becomes -1/128. All right. It is a real number and it is -1/2. Okay. Evaluate this expression without the use of a calculator. When you have a power that's a rational power, this is the same thing as a radical. That's the big kind of like connection between the previous section P.2 and this section P.3, is that radicals are actually just powers. They have the same properties as powers, so they work the same way. And the way it works is the fraction, the denominator, that is the power on the radical. Now, because of the way this thing is, so 125, the 2/3 is the same thing as 2 times 1/3. These are the same things. 2 times 1/3 is 2/3. Now, we can write this in two ways. 125 squared to the 1/3 and 125 to the 1/3 squared. The reason why I'm writing this is because the 1/3, that's a radical, and the 2, that's just the power on the 125. And to simplify this thing down, there's actually an easier way of doing it than the other way. In general, it's easier to take the radical first and then square it. That's because radicals make smaller numbers. So because a power to a power is multiplication, that's why these are all the same thing. You can write them either way, but they all give you the same number in the end. However, this form is a little bit easier. This is the same thing as saying 125 to the 1/3. That's the same thing as the cube root of 125. And then squaring it. This one is where you take 125 squared, and then you take the cube root of that. This method is easier because the cube root of 125 is 5. And 5 squared is 25. So I could do that without a calculator very easily. This method is 125 squared first. And I don't know what that is. That's a very large number. I'd have to use a calculator to do that. But this method is a lot easier. And they show that by having you write it as a radical first. So I can write the cube root of 125 and then squaring that whole thing. And I just found the full answer is 25. And that's correct. Okay, we have fractional powers here, and we're trying to simplify this expression down to lowest terms. However, I just told you that these are, in fact, the same properties as exponents. They have the same properties. So I can split this up. 49 and 7. 49 divided by 7 is 7. And we have like bases that are dividing. So we subtract the exponents. X to the 1/4 minus x to the 1/6, or sorry, x to the 1/4 minus 1/6. These are fractions. We can combine fractions by making them have like denominators. Multiply 4 by 3 and 6 by 2. That'll give me 12. 3 over 12 minus 2 over 12. I wrote 16 there, it's 12. And that gives me 1 over 12. Or in other words, the 12th root of x. But we don't need to worry about that. It says use fractional exponents only. So the 1 over 12 is fine. X to the power of 1 over 12. That's correct. It tends to work out that the exponential form of a radical I think is easier to work with. Sometimes, however, the radical is easier to see what's going on. Just the context will dictate which way you should go. Okay, this one we just need to simplify this thing all the way down. We have x to the negative 5/8, y to the 1/3 over x to the negative 1/8. And that whole thing is to the negative 6 power. So once again, this is very similar to the P.2 work. All I'm going to do is have like bases. We have x and x. So this can kind of be shifted over some. We have that kind of divide there. This is just over 1. And now I have like bases that are dividing. So I'm going to subtract negative 5 over 8 minus negative 1 over 8 is x to the negative 4 over 8. But that reduces down to 1/2, so negative 1 over 2. And the y to the 1/3, that nothing's been done to that, so that's fine. Now I can distribute the negative 6 into each of the powers. Negative 1/2 times negative 6 is x to the 3. And 1/3 times negative 6 is negative 2. It doesn't say anything about positive exponents, so this should be our final answer. Power of negative 2. And it's correct.